Well, we use the word in reference to the laws of physics that apply in the microscopic world at the level of individual atoms, individual electrons, elementary particles, where physics is qualitatively different than what we experience in our everyday lives. You ever been to the beach? You see waves coming in. Why do the waves have characteristics? Speed. That's all classical physics. Send a rocket to the moon. There's no quantum physics in that.
We're discussing right now quantum world, which is at the very smallest scales. The elements of reality down at that level are not described by what we're used to, which is the momentum of something or the position. If you were to go and ask the same question at the microscopic level, at the quantum level, then things break down. So things are different there.
And that's a big part of why we're interested in this whole subject. Can we take this quantumness of the microscopic world and blow it up to larger and larger sizes, manipulate them in a way which is highly controllable to get them to do what we want them to do? If you have a quantum system, that quantum computer can do things, can perform tasks that we couldn't hope to perform with ordinary digital computers. You can't dream of doing it. So when we think about how quantum information is different from classical information nowadays, we're thinking about this intrinsic randomness, the uncertainty principle, and also about entanglement. Classical information we can express in terms of bits. You can take any amount of information and just write it as a string of bits. And in the quantum case, we call them quantum bits or qubits, and they're different from ordinary bits in some fundamental ways. So a classical bit, I can write a 0 or a 1 on the table, and everybody can look at it in the same way. But in a quantum bit, there's more than one complementary way to look at it. So you can kind of picture it this way. You've got a box, and you can put an object in the box. In the quantum case, there's more than one way to open the box. And you've got to make a choice. If you open door number 1, you'll never know what would have happened. It cannot be known what would have happened if you had opened door number 2 instead. Those are incompatible things. That's something really new compared to classical physics. That's what I mean when I say it's really intrinsic randomness. It's not that there's some record somewhere, but you haven't looked at it yet. There's no record. It hasn't been decided yet whether it's going to be 0 or 1. It's not until you make the observation and open the door that it becomes the value of this bit. Maybe it's a 0, maybe it's a 1.
The randomness comes from the ability of quantum states to be in a superposition, to be both in the state of 0, of definite, like say spin up or some like particle, and also a spin down state. What if there were not just numbers, there were waves, right? And you can like put together 2 of these waves, and you can think of having half of a 0 and half of a 1. So whenever you measure it, you will end up getting half of the time the 0 and half of the time the 1. So superposition is fundamental for that randomness.
If I flip a coin, I don't carry coins in my pocket anymore, or I'd flip one. I flip a coin and then I cover up the coin as soon as it lands. You don't know whether it's a heads or a tails, but it's either a heads or a tails, we just don't know yet. That's not a superposition. That's a probability distribution. But if we have the most complete description of the system that is possible, compatible with quantum physics, like when I prepared the state and when we open door number 2, we don't know whether it was a 0 or 1, that's superposition, because that's really intrinsic randomness instead of probability associated with ignorance.
So it takes 2 to tango in quantum entanglement, right? You cannot just have a single qubit and say, oh, it's entangled with what? So you need 2 qubits, at least.
The reason these quantum correlations are different than classical correlations is because we have these distinct, incompatible ways of observing the system. Classical systems can be correlated. We can flip 2 coins and they're either both heads or they're both tails. No big deal. But there's just one way to look at that coin. The qubits are different. We have these 2 incompatible ways of looking at them. They have 2 ways to be correlated, either the same or different for 2 different sets of doors. Those are altogether 4 possibilities, and that means the correlations are richer, they're more interesting. And the richness of the correlation increases very markedly as you increase the number of parts or add additional qubits. If you have just a few hundred qubits and you want to write down a complete description of all those correlations among those qubits in terms of classical bits, you'd have to write down more numbers than the number of atoms in the visible universe.
It's one of these things like, I don't know if it was Faust that said it, that achieving perfection is hard, but remaining perfect, that's impossible. A lot of what we're trying to do also create things that are stable, right? Because you can have the most exotic quantum state, but unless you can probe it, measure it, evolve it in some way that you want, steer it, it's going to be useless.
There's a central problem, and that is if you're running a quantum computation, if you're performing a sequence of operations, processing of quantum states, that has to be very well concealed, not just from you and from Spiros and from me, but from the whole outside world. Classically, there'd be nothing wrong with looking in every time step what the state of the computer is. That wouldn't prevent the computer from getting the right answer. But quantumly, if we keep looking at the computer, that will destroy these delicate superpositions. It's a secret computation until the end, when we're finally ready to get the result out. We make a measurement, and then it's okay to tell everybody what the outcome is, to broadcast it to your friends. But we can't be looking at the computer while it's performing the computation. If we ask it afterward, what did you just do when you factored that huge number, it should say, I don't remember, because there was no record left behind of what it was doing at intermediate stages of the computation. And this is what makes it so challenging, because we can't allow any leakage of information from the computer to the surroundings. That would destroy the quantum computer. That's what we call decoherence. It's the big enemy. There's a whole quantum world out there which is largely unexplored, because it's only now, within the last decade or so, that we are developing the technological capability to scale up quantum systems, to manipulate them, and we're not exactly sure what that's going to lead to, but we think it's exciting. And I do get excited.